Hi everyone, we're Team 4 and I'm Jiawei Liu. We are here to present the overview and an illustration of one remediation method for treating the underground contaminant site. Now nowadays, except for those superfront sites, many places were contaminated by different forms of contaminants, including landfill, agricultural use, and industrial emission. A lot of land and soil has been contaminated. A lot of those contaminants permeate through the ground layer and went into the aquifer. The dispersal of those contaminants can cause huge pollution to the groundwater system and also the local soil system. Due to the hard control of the movement and the behavior of the contaminants underground, many remediation methods were developed to solve this problem. This relates to water preservation, soil protection, and animal protection issues. And of course, for human safety, we need safe drinking water, so we need to prevent this pollution in our underground water system. Back to the main topic, here's the method we want to talk about, soil washing. But be careful before we first get into the introduce. The soil washing includes in situ and ex situ methods. Both are different approaches to do soil washing. In situ means that the operation is completed underground at the sites. Ex situ means the operation is done outside the sites, which means that the contaminants will be extracted and treated at ground facilities and then will be placed back to the site. Here we are talking about soil washing in situ, or many want to talk it like soil washing in situ method. This is what we want to talk about for the first. And now we get into the soil flushing. The right side is the picture showing the mechanism, simple mechanism about the soil flushing and about a little bit of information about its field implementation. I will talk briefly about it, but more detailed things will be illustrated in the second part. As you can see here, the blue arrow means the flushing solution will be injected by the injection well into the ground, and the down gradient will drive the solution to the contaminant site. And after the treatment time, the extraction well will extract those flushing solution with the contaminated removal up to the ground facilities into a large column tank, which is a storage tank, and then will be delivered to a round tank for wastewater treatment. And this is just a simple illustration for this field implementation and about its mechanism. But the more important things we want to talk about in this slide is why soil flushing. There's a few bullet points here, and the first one is that we don't need to do excavation, handling, and transportation operation for soil in situ soil flushing, and it will have less cost, and the flushing solution can be easily recycled through after the treatment of wastewater treatment system, and it is more sustainable, cost less, and it will more environmental friendly for this operation process. And it is most effective in the permeable soils. And the soil flushing can stop migration of contaminants and the toxic substances to the uncontaminated area through the aquifer. So that will prevent the dispersion issues that I'm talking about in the last slides. And it is more nature preferred because not like the ex situ soil flushing, you need to soil washing, sorry. You need to dig out a big hole to remove all the contaminated soil out and then to do a series of treatment on that. That might cause you to destroy the terrain and destroy some ecosystems, small ecosystem at that site. Maybe you not be able to notice it. So potential environmental harm will be associated with the ex situ operation, but in situ, we don't need to do anything changes about the terrain and any strata structure. So that's how it calls nature preferred. And of course, the last one is the less energy consumption. We don't need to do the less of the excavation, less human resources, and less machine uses, so less energy consumption. And here we want to briefly talk about the behavior and the mechanism, the particle scale, the mechanism in the soil contaminant site. And the soil is the contaminant is contracted in the soil between the soil particle with strong interfacial surface tension forces, and the flushing solution which is being injected into the contaminant sites is for reducing the surface tension, and will recombine them into the solution or dissolve them into the flushing solution so that we can extract the solution with the contaminants and then treat them. So here you see it's aid the pump and treat and primary recovery for NaPl, and once the NaPl is not at free phases, the mobility ratio will be greater than 1, and this is the formula for mobility ratio that we show here. And soil flushing will be targeted to decrease interfacial tension, as I said, between water and NaPl. And it will increase the NaPl mobility so that we can it will be more easier than us for us to remove the NaPl from the interparticle places between the soil particle. And the secondary recovery will be NaPl plus some aqueous solution produced. And the water flooding type approach will be used in pump and treat when the mobility is smaller than 1. And also, when the ratio is greater than 1, not only we need to use the mobility ratio, and we need to decrease the capillary pressure by adding some agents, so that it can be more easily for us to extract those contaminants. Here is the important part. I will say that it is the most important part for the whole mechanism of the in situ soil flushing. It's the flushing solution. There are many types of the solution, like including acid-base and surfactants, and like to use many different kinds of flushing solutions will depends on the condition of the sites, the condition of the specific contaminants, and also the cost and the applicability that will be talked about in later slides will also influence these choices. And all the flushing solutions, as I introduced in the previous slides, will be treated in the wastewater treatment system. And due to the usage of different flushing solutions, it will slightly change the wastewater treatment system, like how to treat it and how it processed. In the next slides, I will introduce it for some main types of the flushing solutions with some example and how it works. Here is the table that I present the details for the washing agents, which is also the flushing solution. The first one is the most commonly one. Everybody knows that, the water. And the water can be used to treat hydrophilic or soluble heavy metal salts. The metal will dissolve in the water, and the water will be extracted to the upground wastewater treatment facilities, and then will be recycled back into the operation. And this one is an acidic solution. An example for that is nitric acid and hydrochloric acid. It can be used to treat metals or some basic organic materials. And this one is the basic solution. The normal basic solution we use is sodium hydroxide, and it can be used to treat metals such as zinc, lead, and tin. And also the organic one is the phenols. And chelating, it has an example for ethylene diamide tetraacetic. It's also called ADTA, and it can be used to recover some certain metals. And the next one is the reducing agent. The example for that is hydroxylamine hydrochloride, and it can be used to treat multiple types of metal compound and impure metal. It includes iron, manganese oxide, and insoluble heavy metal compounds. Co-solvent is a commonly used agent, and it is a solvent mixture, and most field implementation use alcohol as a solvent to do the treatment, and it is very effective in treating the organic contaminants. And surfactants, there are groups of hydrophobic and hydrophilic chemical components that are very effective in treating hydrophobic organics. This is the overall description of this several types of washing agents. To choose washing agents, as I said, it depends on your many different types of conditions in the sites and for the pollutant itself. So this is an important decision in the whole process of the in-situ soil washing, and if we do not choose it wisely or carefully, that might destroy, or the soil flushing process might not be work. The one I want to talk about more in detail is the surfactant and co-solvent flooding. It is in-situ soil flushing using the solution with both surfactant and co-solvent. And the right side, the picture shows how the residual NaPl sits in between the soil particle, and also illustrate again about the field implementation information about how the injection well, like using the down gradient to move the flushing solution through the contaminant sites and extract it out from the site. Well, back to the topic. For the surfactant and co-solvent flooding, we commonly use solution which contains about 5% surfactants and 90% ethanol, which is also one type of the co-solvent. And the famous soil flushing method, this is a really famous soil flushing methods in the early 1990s, and it is really good at treating DNPL sources. And the one main advantages for using this method is that it is most amenable to homogeneous subsurface systems, and because it have sufficient permeability to permeate the aquifer and permeate the contaminant sites to catch all the contaminants. And it is based largely on part of the enhanced oil recovery research in very previous years, so it is a really basic founded solution to in the in-situ solution soil flushing process. Here we want to talk about more detail about the surfactants. First one say that it contains both hydrophobic and hydrophilic groups, and it can accumulate in the flushing solutions and in the contaminant sites at the interface, and will alter the interfacial properties between the soil particle and the contaminants. So in this case, it can significantly reduce the surface tension between the two phases. Like for the NaPl, the interfacial tension can be reduced from 49 per centimeter to 59 centimeter. And it is a large reduction of the interfacial surface tension. And it contains three main groups for surfactants. One is anionic, the second one is cationic, and the third one is non-ionic. First one is anionic surfactants, and it is really sensitive to some electrolyte species like the salt, sodium hydroxide. And so before we use the anionic surfactants, the salt concentration level will be carefully monitored at the contaminant sites and also the underground water system. The cationic surfactants will be used to modify the mineral surfaces, which can be more easily for us to remove the heavy metal salts and heavy metal compounds in the contaminant sites. The non-ionic surfactants are not sensitive to pH and salt concentration, which means that it is more amenable to use than the anionic surfactants in some certain conditions. And still, we have more types of surfactants. One is the amphotetric surfactants, and the other one is the biosurfactants. The right side shows a picture about the graph about the surfactant concentration and the solubility of organic compounds, the behavior of the solubility of organic compounds in the treatment process. As you can see at the point at the critical initial concentration, the solubility increase largely after this point, and which means that the surfactants start to work and have effects on the organic compound, and because of the reduction of the solubility, all the organic compound will be attached to surfactants and then will be extracted with the flushing solutions to the upper facilities to be further treated. The other one we talk about is the co-solvent. It is commonly more than 90% co-solvent will be contained in the treatment solution agent. And there's a method which was investigated to apply in altering the sorption and desorption behavior of hydrophobic organic compounds. And its enhancement of solubility with the presence of the both miscible and partial miscible co-solvents is performing really great. Alcohol was investigated as really commonly as a low molecular weight homogeneous series for co-solvent usage. It is less dense than water, and it makes it more have more better recovery performance and delivery performance for those contaminants. And ethanol, as you can see in the last slide, ethanol is also an commonly used species of co-solvent, and it is completely miscible in water, so that it can improve largely the mixing of with good delivery of the single fluid phases. And the most important things for co-solving is that it's really low cost associated with that. We just need to use $1 or $2 to buy a gallon of the co-solvent solutions.
Influencing factor is highly related to the soil property, like the permeability and composition, and there are 5 influencing factors. The first one is high permeability soil. High permeability will allow the fluid to move quickly through the rocks. It requires a huge volume of fluid to go into the surface for effective contact with the contaminants. Treatment reagent solution injected into a high permeability granular soil tend to infiltrate the pore space more uniformly when a sufficient quantity of solution is injected. In this case, it may use lots of fluid, but is easy to treat. The second factor is low permeability soil. On the other hand, the low permeability means the water is harder to go through the soil, so we need more injection events. Even though it requires less fluid to treat the contaminant sites, but it's harder to remove the contaminants. And the third factor is histosol. Histosol are the soil that has high organic carbon content and poor drainage. Some of the fluid will have the potential in reacting with the organic material in the soil, and it would require additional fluid to fulfill the task. However, the poor drainage property constrains the amount of fluid we pump in. As a result, we need to monitor the volume of injection during the pumping process. It is going to be the challenges for high organic carbon content and poor drainage soil. Next factor is heterogeneous soil. A heterogeneous mixture is not uniform in composition, but is proportional of the components vary throughout the samples. While the contaminants may have migrated primarily through the higher permeability soil feature, the lower permeability soil typically exhibit a greater ability to retain many contaminants. As a result, retention of the contaminant in soil feature had limited accessibility to inject the material due to the preferential flow of the fluid through the higher permeability soil. In heterogeneous formation, site characterization is even more critical to determine more precisely where the contaminants are located relative to the various geology features, so that those areas can be targeted for remediation. The last factor is bedrock formation. Groundwater flow in bedrock formation is primary fracture and bedding plane control, although weathering and mineral dissolution may add additional pathway. Detailed site characterization is required to determine contaminants distribution and migration pathway, and subsequently injection well design and location. The investigator is remain that in sedimentation rock formation, contaminant mass may be primarily held within the low permeability rock matrix. At opposite to the local fracture system, injection volume and extent of the influences will vary significantly based on the specific bedrock formation.
Hi, I'm Yusuf, and I'll be talking about the field implementation of in situ soil washing, also known as soil flushing, which is different from ex situ soil washing, which we'll be talking very briefly about in the end. So this figure here, it shows briefly the process, and I'll show it to you again once I talk about things in a bit more detail. So we must have a way of injecting the additives and of extracting both the additives plus the contaminant. So we must always be having at least two, but we can also be having a three-spot pattern where there's either one injector and two producers, or two producers and one injector. There's similarly a five-spot pattern. There's also seven-spot patterns. The wells can be horizontal or they can be vertical. We determine the number of wells, their locations, and their depths based on the field study, which is done prior. Understandably, we must be having a very good idea about the site geology before doing anything, and we need to know about all the about hydraulic gradients, flow barriers, etc., so that we know that the additives are going in the right direction, and then the extraction wells are actually able to bring in as much contaminant towards them as possible, and then that the contaminant is not being lost elsewhere, further deteriorating the problem. We need plentiful access to water so that we can be making our alkalis, surfactants, solvents, etc. Of course, we need roads to bring in the machinery. Drilling equipment depends whether we have auger drilling or some kind of deeper wells, then which also need casing, etc. We need to be careful about what time of the year we're doing this, because additives can be sensitive to cold weather. And in some simpler cases, we can simply spray the if it's not too if it's not too deep, we can just spray the additives rather than injecting them via a well. So we have mixing tanks and pumps, and it's important to know that the additives, one additive can only be treating one kind of contaminant, We can't have one recipe for a number of different contaminants. So the the additives, their injection rates are determined based on the field, and then it travels along and it reaches the extraction well, both the additive plus the contaminant, which is now called the elutriate. On the surface, we then have a separator and some waste facilities. Hopefully, we're able to recycle the additives, and the contaminants are then treated by ion exchange, volatile organic compound stripping, neutralization reactions, gravity settling, where the sludge is allowed to settle so that the waste can be treated accordingly, or flocculation, where the contaminant turns to colloids, which turn to flakes, which are then removed. Um, I'll show you this again so that we are injecting down the additives. This increases the mobility of the contaminant, which then flows as a free phase towards the extraction well or wells, which are brought into the surface. We have a separator. We recycle the washing solution, and we have a treatment facility. We might also be having fumes, which are also treated according to the standards. XC2 is almost the same, except that instead of doing it in the subsurface, we first excavate the soil, bring it on the surface, remove all the big rocks via jigging, screening, or hydrocycloning, and then it's the same treatment method, same washing, same additives, and then the same waste treatment. And the washed soil is then mixed with the bigger rocks, and it's taken back and it's refilled. So there will be a few case studies ahead which will make this all much clearer for you. Thank you for listening.
The first case study that we'll talk about today is the soil washing at the King of Prussia Technical Corporation Superfund site. This is located in Winslow Township, Camden County, New Jersey. It is a 10-acre abandoned waste disposal and recycling facility, and as you can see from the figure on the right, the nearest residence is 1 mile northeast of the site. The nearest surface water body is the Great Egg Harbor River, which flows 1,000 feet southwest of the site. The King of Prussia Corporation operated this facility from 1970 to 1974, where in 1974 it was shut down. During its operation, there was over 15 million gallons of acids and alkaline aqueous wastes that were processed at the 6 different lagoons on this site. Um, there were also past waste handling and disposal practices at this facility, as well as suspected illegal dumping of trash and hazardous materials after the facility ended up closing, which resulted in organic and inorganic contamination of the site soil, sediment, and groundwater. Samples of surface soil, subsurface soil, and sediment were collected to characterize the soil next to each of the lagoons, the sediments in the soil, and the sludges in the lagoons and the adjacent area. Um, all of these samples allowed us to determine that the primary contaminant group were heavy metals, and the primary contaminants in these areas were beryllium, chromium, copper, nickel, and zinc. The constituents of concern that was mainly worked at for this soil washing site was chromium, copper, and nickel. Chromium was found at levels up to 11,300 milligrams per kilograms. Copper was found at levels up to 16,300 milligrams per kilograms, and nickel was found up to 11,100 milligrams per kilogram. Alternative Remedial Technologies Incorporated was the company that designed and operated this soil washing plant in 1993. To select which type of excavation was used, they used X-ray fluorescent or XRF to determine which soil needed to be treated. And then sludge and soils at this site were blended to maintain an even sludge to soil ratio or mixture. So the way that the selective excavation of the soil and sludge in and adjacent to the lagoons and the swale area involved many steps, including excavation of clean, overburdened soils and staging and or the transportation of material to the stockpile area, excavation of contaminated soils and transportation of contaminated soils to the screening and blending area, then X-ray fluorescence analysis of the contamination levels in the trench bottom soils and backfilling of the clean trench bottom with XRF confirms clean material. And then this allowed us to blend everything for that even mixture. Next part, the soil washing system was actually designed and constructed by Alternative Remedial Technologies Incorporated. This unit consists of 4 different units: screening, separation, flotation, and sludge management. The screening process screened out the gross oversized fraction from the pile of material to be treated by means of a hopper and a vibrated grizzly. Um, the separation aspect separated the screened soil and water slurry into coarse and fine-grained material through the use of multi-stage hydrocyclones. Froth flotation removed the contaminants from the coarse-grained material by means of air flotation treatment units, and sludge management treated the overflow from the hydrocyclones. All of this you can see in the figure to the right, which kind of describes the entire soil washing system. And this system had a rated system throughput of 25 tons per hour. As for results of this soil washing system, it was quite successful. Approximately 19,200 tons of contaminated soil and sludge were treated during this operation. The soil washing system achieved the specified soil cleanup levels for all 11 metals, and treated soil was used as backfill at the site. Additionally, all of this was achieved in less than 4 months. The total cost for this application was $7.7 million, including off-site disposal costs for the sludge cake. Additionally, selective excavation reduced the overall costs for the application by reducing the amount of soil requiring treatment by a factor of 2. So overall, this was a pretty successful soil washing unit and a pretty famous one at that. The next case study we'll go over was completed by the Claire Technology Demonstration Project, where they did a remediation trial at the Avenue site in Chesterfield, Derbyshire, United Kingdom. This remediation trial was treated at pilot scale using soil washing at the Avenue Coking Plant and Chemical Works, which was constructed in the 1950s and operated until 1992. During its operation period, 18 million tons of smokeless domestic fuel was produced, along with many, many byproducts. This led to extensive land and groundwater contamination associated with tar lagoons, waste tips, site soils, tanks, sumps, and redundant pipe work. Um, the contaminants of this project include coal tars, lime sludge, acids, phenols, PAHs, VOCs, spent oxide, um, substances with ammonium, heavy metals, and asbestos. For this specific trial, materials from 2 different areas of the site were chosen to undergo soil washing, and that was the former waste tip, which was contaminated with organic and inorganic contaminants like PAHs and cyanides, and the plant area, which was contaminated with organic materials such as phenols, petroleum hydrocarbons, and aromatic hydrocarbons. The pilot scale trial was carried out in November of 2001, and it lasted a total of 1 week for the testing. The capacity of this soil washing treatment system was between zero 0.5 to 1.2 tons per hour. 20 tons of material was tested for the waste tip, and 10 tons of material from the plant area, which was pre-screened to 75 millimeters, was also tested for the plant area. As you can see from the figure to the right, there are photographs of a selection of modules in the soil washing process. The first one is the feed hopper with built-in grizzly screen, and this removes coarse debris greater than 80 millimeters. The next one is the conveyor magnet and vibrating screen. So the electromagnet removes iron-based debris, and the weighing cell and conveyor belt with speed control controls the feed rate to the process. Additionally, water sprayed vibratory screen at 2 millimeters apertures disaggregates the soil and removes the oversized fractions. There is also a primary cyclone, um, which is used separately or in series, and this segregates the material that's less than 2 millimeters into a just discharge product containing mostly sand-sized materials and one containing silt and clay. In addition, hydrocycloning also removes a significant proportion of water from the sand-sized discharge product. This partial dewatering to 60 to 70% water by weight improves the efficiency of the downstream scrubbing process. Next shows a spiral or strew classifier, which is compared to hydrocyclones alone. The spiral classifier removes more organic material. Additionally, the gentler action of the spiral classifier limits the potential for emulsifying any free phase oils. Next is shown the spiral concentrator, which is a single spiral with 3 turns and 3-way product splitter, which uses differences in specific gravity to segregate. So a low specific gravity product, which contains most of the contaminants or organic, light minerals, coal, oil, tar, etc. A heavier SG product, which, if clean, is dewatered as a final product. Alternatively, if still above the cleanup target, is further processed by froth flotation. And then a middlings product, which is either repassed through spiral concentrator or treated using downstream froth flotation to remove the contaminants. The same picture also shows the secondary cyclone, which is a 3-inch stub cyclone or hydrocyclone, overflow to carrier, underflow to flotation conditioner, and this removes the abraded contaminated material released from attrition scrubbing the sand-sized material. It also shows a dewatering sieve. So this reduces the water content of the clean sand slurry to about 75% solids by weight. The next photo is a sieve bend, which is a 500 micrometer screen with a cut point of 200 micrometers. And as a part of stage dewatering process, it removes less than 250 micrometer material from the light fraction of the spiral concentrator. The photo below in the middle is a twin flotation unit or froth flotation units, and these just remove contaminated coal and low specific gravity material from the relatively clean components. And the last component in this picture is the jig. Now we can start talking about the results of this trial. So for the waste tip material, we found that different parts of the soil washing system has varying rates of efficiency in contaminant removal. For the wasted material, PAHs and cyanides were the main constituent of concern. We saw that 75% of this material was less than 2 millimeters, and subsequent treatment of gravel size fraction with the mineral jig removed 97% of the PAHs. Additionally, for the sand size particles, which are less than 2 millimeters, the spiral concentrator and froth flotation removed 38% of the PAHs, and it was estimated that the soil washing could produce a contaminant depleted product from the wasted material, which meets the site specific waste recycling requirements. This material represents 40% by proportion of the total organic material. And lastly, we will talk about the results of the plant area material. So, for the plant area, PAH was the main contaminant of concern. The materials or particles greater than 2 millimeters, followed by mineral jigging, produced 76% total contaminant depletion. The sand size particles had the highest efficiency achieved by density spirals, which reduced the PAH concentrations by 73%. And the cost for the full scale soil washing was about 20 to 25 euros per ton, which ends up being about 21 to 27 US dollars per ton. So overall, this was a pretty efficient soil washing system developed for this trial.
Applicability of the soil washing. Commonly, it can be used in non-complex and high-parameter soil and to wash the soil for the organic compounds, and both of two same or complete volunteer can remove from the solvent, and also will be used in the fuel like gasoline or diesel, something like that, and also used in the toxics or the heavy metal, which is chelating agent, mostly used in the not degradable toxics because it cannot removable by the common way, other way, like something like that. And mostly it's used in the different from the different chemical behavior, such as after industrialization or the modern agricultural practice or something like the mining activity. It will be using that. And also it has a lot of like the limitation, like as we talked about before, so it's used in the non-complex soil. So if we have the complex wasting mixture, so like the metal with organic, something like that, makes the fluid very difficult to wash. And also high human contact in the soil, it will be required more pre-treatment, and also the stream will be required treatment in demobilization, and also additional treatment steps may be required to address higher size levels of washing solvent remaining in the treatment radiation or residual, and also it may be hard to remove the organic absorbent onto clay-sized particles.
The key cost information and cost analysis are based on the 2016 version of the Remedial Action Cost Engineering and Requirement Software. Soil permeability and depth to groundwater are the two key elements to have a strong impact on the cost. Soil with lower permeability are more recalcitrant to soil flushing. Thus, it will take a longer remediation time to lower the concentration of the contaminant. In other words, the cost will significantly increase with increasing time. The second factor is depth to groundwater. The deeper a water table is located, the higher the cost it will be. Let's look at the table. A sample shows a small site can treat 1,388 cubic yard, while a large site can treat 5,550 cubic yard. Is the more we treat, the cheaper the cost it will be. Based on the difficulty, an easier case would be cheaper than a difficult case. For example, treating a high permeability soil is easy, but treating a heterogeneous soil is more difficult. So, for easy and small site, the cost is $32 per cubic yard. For difficult and small sites, the cost is $49 per cubic yard. For easy and large sites, the cost is $18 per cubic yard. For difficult and large sites, the cost is $27 per cubic yard.